Well, good morning there, Advanced Chemistry. This morning we're going to start learning target 4.5, which focuses on neutralization reactions. We're going to talk a lot about buffering and titration, and hopefully this will be really valuable stuff for you down the road. So let's start by talking about what a neutralization reaction is and the definition. So a neutralization reaction is going to take place between an acid and a base. So those are the two things that are reacting together, and it is going to form a salt and water. So it's called a neutralization reaction because the acid and base are going to neutralize each other as much as possible, leaving a salt and water because of that reaction. Now a salt, if you think of a salt as being a cation and an anion, so that means it's an ionic compound, that cation is going to come from the base that is reacting in the neutralization reaction. And the anion is going to come from the acid in the neutralization reaction. So that's important to know. If I was going to do a quick example here, if I did a strong acid and a strong base, I could use hydrochloric plus sodium hydroxide. My salt, this is a double replacement, my salt would be sodium chloride plus HOH, water. So you can see the sodium comes from my base, Na, and my chloride comes from my acid, HCl. So the cation in a neutralization reaction's salt is going to be from the base. The anion is going to come from the acid, and that's important to know as we go and discuss what's coming next. So our goal today is going to be to look at a salt, any salt, like NaCl, and to predict if you dissolve a salt into water, so if you make an aqueous solution of a salt, would that solution, resulting solution, be acidic, basic, or neutral? So that's our goal for today. So let's look at how this works. I've had up here, last year, for some reason, this was a very confusing thing to my advanced chemistry students. So I tried to this year give you some steps for predicting the pH of solutions of salt. And this is known as a salt hydrolysis. This means hydrolysis, breaking of water. So in other words, a salt's interaction with water. So what we need to do first is to find the parent acid and the parent base of the salt. So if I have a salt, for example, let's take, NH4Cl. Here's a salt. So we need to find of the salt the parent acid and the parent base. So to do that, remember that the cation comes from the base, or the parent base. So that's where this came. If you think of this as the daughter, the parents are what made it. So NH4 comes from the base. So what base resulted in NH4? So in other words, if you think of this as Bronsted-Lowry acid-base theory, if this was the conjugate acid, what would the base be? So this is NH4 plus 1, so our conjugate partner would be NH3. So in other words, NH3 picked up an H plus 1 and made NH4. So our parent base, I'm going to put PB, parent base is NH3. Now I've also got Cl minus 1 here, so I've got NH4 plus 1 and Cl minus 1. And remember, the anion comes from the acid, anion acid. So if this were the conjugate base, what would the acid be? It would pick up an H plus 1, and the parent acid was HCl. So we look at those parents. So those two things reacted together, NH3 and HCl, and that should make NH4Cl. So So we need to be able to identify those things. Now number 2 says the strength of the conjugate acid or base in the salt is opposite of the parent acid or base. And we've talked about this week. So in other words, if NH3 is a really weak base, it has a very small Ka, that means, or excuse me, Kb, because it's a base, then that means NH4 should have a pretty high or higher Ka. So if you have a weak base, that means its conjugate acid is going to be strong. And remember, that's because of that relationship to Kw that we've talked about. If you've identified the component of the salt as strong, it will react with water to form an acidic or basic solution. If it's weak, then it will not. So these are just some guidelines for predicting. So we're going to do a few now to show you how to get the hang of this. The first couple don't make sense, just stick with it. Okay, so there's the example that we just talked about. So we went through step 1, which was to identify the parent acid and the parent base. We said that was going to be NH3 for our parent base and HCl. Now, what we've said is that NH3 is a weak base, which means that NH4Cl is going to be a strong acid. And we've said that HCl is a strong acid, so Cl minus 1 is going to be a weak base. So now we can ignore these things because what we've got in solution is something that's acting as a strong acid and something that's acting as a weak base. So anything that's weak we can ignore, but anything that's strong, we need to show that reaction to see what happens. So NH4 is going to react with water. It's a strong acid. So what we're going to get is, as a result, we are going to get a lot more H3O+, a significant amount, so this solution will be acidic. So dissolving NH4Cl will result in NH4 plus 1 reacting with water to increase the amount of H3O+, a significant amount, which means we're going to have an acidic solution. Let's do another one. Okay, this time I have LiC2H3O2. This is lithium acetate. So step 1 is to find your parent acid and base. So remember, your cation comes from your base. So Li's base was LiOH. It's an Arrhenius base. LiOH is a strong base, which means that Li as an acid is very weak. Since it's a weak acid, we don't really need to worry about it for reacting with water. C2H3O2 minus 1, its parent acid is acetic acid, HC2H3O2, which is a weak acid, which means that C2H3O2 is going to be a strong base. That means that it is going to react with water, so we'll show that down here. C2H3O2 minus 1 plus water, if it's acting as a strong base, what it should do is pick up a hydrogen and a charge of plus 1, making it neutral, and we will have an increased amount of OH minus 1 in solution, which means that this solution will be basic. Alrighty, see what else we got here. KCl. So once again, first step is to identify our parent acid and parent base. So K, being the cation, is from the base, so that parent base was KOH. That's a strong base, which means this is a weak acid. K plus 1 is a weak acid, so we don't need to worry about K. Cl minus 1 came from HCl, which is a strong acid. This is a strong acid, that means Cl minus 1 is going to act as a weak base, which means it's not going to do anything. So in other words, Nothing's going to do anything to the water that's already there. So this dissolving, if I can spell, is going to form a neutral solution. Example 4 here. Here is our salt. This is ammonium bicarbonate. NH4 comes from the base NH3. NH3 made NH4. So it came from, it might actually make more sense to draw these arrows going the other way, I guess, because this is a parent and this is what it formed, but whatever floats your boat there. So NH3 is a weak base, which means that NH4 is a strong acid. So we are going to need to worry about that guy. HCO3, HCO3 comes from H2CO3, which is carbonic acid, which is also a weak acid, which means HCO3 is going to be a strong base, which means it is going to mess with the water. So NH4 plus 1 is going to mess with water to form NH3 plus H3O plus. However, HCO3 is going to be acting like a strong base with water, and that means it's going to be picking up an H and leaving behind an OH minus 1. Now, because these are happening in a 1-to-1 ratio here, we've got a 1-to-1, that means that for every time this happens, you're going to have an H3O plus and an OH minus 1 canceling each other out. So this will also be a neutral solution, just as example 3 was. Okay, so with that, we're going to stop, and I'm going to have you guys try some of those. Remember to go through your steps, asking yourself if it's going to have a strong acid parent, strong base parent, and then identifying the components in solution, attempting to predict what's going to happen in those solutions. So best of luck, give it a try. See you later.